So 16.1, we're really getting into acid-base stuff now, and we're going to talk about pH theory, or how pHs are calculated, what pHs even mean. We probably have a little bit of experience with pHs, and know that low pHs mean things are acidic, and high pHs mean that things are basic. So our knowledge right now of pH, so it's probably something like this. Here's a pH scale. And we've probably seen one of these before. We know that a pH of 7 is pure neutral water. And as our pHs, again, get lower, we get things that are more acidic. And as we get higher, we get things that are more basic. And we're going to look at why here and how this calculation is done, what these numbers actually mean. What it comes down to is that all of these things are in water. And so we have to think back to what we talked about previously, that water is really amphoteric. Water is an acid and water is a base. And actually water, if we have a solution of, well, a solution isn't the right word, if we have liquid water is constantly kind of ionizing itself. And so one of the waters acts as an acid, donates a hydrogen ion to the other, which acts as a base and accepts it. So we have a water-water pair here, and what we get is hydronium, and we get hydroxide. Hydronium, by the way, is spelled like this, hydronium, and this is our hydroxide ion. And we'll recognize these, hopefully, that hydroxide is what we see as a lot of the piece that makes a lot of strong bases, right? We see that in a lot of strong bases. Hydronium, well, we don't see that necessarily in a lot of acids, but we see the root of it, which is really the hydrogen ion. And sometimes, just to make things more confusing, we refer to hydronium sometimes simply as hydrogen ions, which isn't really accurate because those hydrogen ions attach to the water. But typically, if there's hydrogen ions in water, those hydrogen ions really become hydronium. So sometimes we use those interchangeably, even though they're not really the same thing. You'll often hear them referring to hydrogen ions instead of hydronium, just because hydronium is sometimes hard to say, and it takes more to write. Anyway, what we have is water self-ionizing. It's forming hydronium, it's forming hydroxide. This happens in water, which you might not like. You think, well, I don't know of any acidic or basic samples of pure water. Well, two things we have to remember. One is that even though that this shows an equilibrium, that doesn't mean the concentrations on each side are equal. Just that the reaction is continuous and it's going in both directions. Truly, for this reaction, there should be a really small arrow going to the right and a very large arrow going to the left. So this equilibrium lies very far to this side, and we make small quantities or small concentrations of both hydronium and hydroxide. So there's small concentrations of them, so we're going to refer to them as concentrations. The other thing we have to recognize is if two water molecules are reacting, any time water produces hydronium or hydroxide on itself, it's important to remember this, that the hydronium concentration in neutral water will always equal the hydroxide ion concentration. Okay, so what are those concentrations? Well, these ion concentrations can be measured. Again, this is for water, and let me define this. This is for water at 25 degrees Celsius, because the concentrations do change with temperature. Typically, as the temperature goes up, water dissociates more and it self-ionizes a little bit greater. But at 25 degrees, measured with a conductivity meter, we'll find that the concentration of hydronium ions is 1 times 10 to the negative 7th molar. So it's moles per liter. Now that's a very small number. That is 0.0000001 moles of hydronium, or we could say hydrogen ions, in every 1 liter of water. So as you notice, that's not a very big amount. That's very, very small. And it's kind of difficult to write and very difficult for people to get their heads around. So typically, again, if we're talking about the concentration of hydrogen ions or hydroxide ions in solution, we don't refer to the molar concentrations. That's just not used. What is used is that pH value. So instead, we calculate it as a pH. Well, how do we get this number, 1 times 10 to the negative 7th, into this number, 7? You'll notice that there is some similarities there, right? There's a common 7. Well, this is how we get it. Really, a pH is a log-based system. And this is a log base 10, which is kind of our typical logs that we have. What we're going to do is we're going to take the negative log of that value. So the pH is the negative log of the hydrogen ion concentration. And really, I should make the right brackets. The brackets mean concentration. So let me fix that. The negative log of the hydrogen ion concentration, or again, hydronium ion concentration, is the pH. That's what a pH is. So if we want to calculate the pH of water, it'd be the negative log of 1 times 10 to the negative 7th. Now that seems kind of complex, especially if you haven't worked with logs before, but again, this is a log base 10. The opposite action of taking a log base 10 is raising something to the 10 power. So those two things cancel. The negative here cancels with the negative here, and guess what the pH of water is at 25 degrees? The pH is 7. So something we already know, that is where this value comes from, is this value is coming from taking the negative log of the hydrogen concentration of water. Now, one thing to notice is if, again, the hydronium or hydrogen concentration is 1 times 10 to the negative 7th, well, so is the concentration of hydroxide ions. What that allows us to do is that's going to allow us to calculate for a constant. What we want to calculate for is the equilibrium constant of water. K is for equilibrium constants. We'll calculate equilibriums going into our next unit. Right now, we're just going to do it for water. The W really is for the water. So we have the equilibrium constant of water. Well, the equilibrium constant is the concentration of the products of a reaction raised to whatever power the coefficient in front is, divided by the reactants, the concentration of reactants in the equation, raised to whatever power is in front of those. So this is how we write standard equilibrium constants, the concentration of the products over the concentration of the reactants. Notice if we write something like that, the more products we have, the bigger the kW, the more reactants we have, the smaller the K, or the kW in this case. So for this one, our kW is, well, what are the products of the self-ionization of water? Let's go back to our equation. We have hydronium ions and we have hydroxide ions over water. Okay, so I'll write it in. So I have the concentration of hydronium ions, or hydrogen ions again, times the concentration of hydroxide ions. Notice there's no coefficients in front, so I don't raise them to any power. So it's these two concentrations multiplied by each other, divided by the concentration of water. Now, since there's two water molecules, I will square this. But what I'm going to do right away is I'm going to get rid of that. Because water isn't a concentration. Notice in our equation, water is a liquid. Liquid is a pure substance, so it can't be represented as a concentration. So what I'm going to do is I'm going to erase this bit on the bottom. So our kW for water really is just the product of our hydrogen concentration times our hydroxide ion concentration. Well, what we just said, and what can be experimentally determined with like a conductivity apparatus, is that the hydrogen ion concentration is 1 times 10 to the negative 7th. Well, the hydroxide ion concentration, because it comes from the self-ionization of water, is also 1 times 10 to the negative 7th. If I multiply these numbers together, it's not really that difficult of math. Our kW is 1 times 10 to the negative, well, if we're multiplying exponents, we add them, the negative 14th. This number, very important. We want to remember this one because this is a constant. That means it does not change. Even if we add other things in the water, this will always be the kW. The product of our hydronium and our hydroxide ion concentration are always going to have to equal 1 times 10 to the negative 14th. This is a constant for water at 25 degrees Celsius. So what does that mean if it's a constant? Well, if our kW is a constant for water, any acid-base solution we have in water, again, the product of the hydronium and hydroxide ion concentrations always has to equal that. So if we have an acid and the hydronium ion concentration goes up, the hydroxide ion concentration goes down. So if we know one, we will know the other. So let's do a sample calculation, something we might have had before. Say we have 0.1 molar hydrochloric acid. Now what I'm going to refer to in the beginning is our only strong acids and strong bases that completely disassociate, completely ionize the water. So what that means is when I have hydrochloric acid in water, this really is not in equilibrium. This truly is more of a one-way reaction. Well, it's in equilibrium, but to a very small extent. So if I take hydrochloric acid, I put it in water, I get hydronium and chloride ions. And if I have 0.1 molar hydrochloric acid, I'm going to make 0.1 molar concentration of hydronium. So let's do a couple things. Let's see if we can use this. So this is a strong acid. This isn't going to work when we have weak acids because they're not going to fully dissociate. We'll do something just slightly different. So this is a strong acid. Let's do a couple things. Let's see if we can't calculate the hydronium ion concentration. Well, that's done, right? Because it's a strong acid, it is the same. Okay? Well, what about the hydroxide ion concentration? Well, again, what we know is the kW is equal to 1 times 10 to the negative 14th. and the Kw is the product of, again, the hydronium, or I'm going to just write hydrogen ions from now on. Hopefully that's okay. Again, it means the same thing. Really, just not really a shorthand, just kind of, I'm cheating a little bit, but it's the hydrogen ion concentration. Well, the Kw, again, if this is 0.1 molar, I'm going to write it this way, 1 times 10 to the negative first. Hopefully everybody can see that 1 times 10 to the negative first is the same thing as 0.1. That times whatever the hydroxide ion concentration, again, has to equal the 1 times 10 to the negative 14th. So what I'll do is I'll divide this side by 1 times 10 to the negative first. That'll cancel. I'll divide this side of the equation 1 times 10 to the negative 1. Now what we do with our exponents is if we're dividing, we subtract them. Minus a minus 1 is going to be the addition of 1. So my hydroxide ion concentration is 1 times 10 to the negative 13th. So notice what has happened now in my equation. My hydrogen ion concentration has shot up to 0.1. Thus, my hydroxide ion concentration has decreased to 1 times 10 to the negative 14th, a very, very small number. Now, one thing we'll need to know is, again, if our hydrogen ion concentration, or hydronium again, is equal to hydroxide like it is in neutral water, well, then we consider our solution to be neutral. If the hydrogen ion concentration like this is greater than the hydroxide ion concentration, well, then of course we have an acidic solution. And if we go the other way around, we have our hydrogen ion concentration, and it is less than the hydroxide ion concentration, we're going to have a basic solution. Now again, what we sometimes do is, because sometimes people get confused when we have these exponential numbers, and it's difficult for them to kind of figure out which is larger and smaller. So again, a lot of times what we'll do is we'll calculate this into a pH. And so now what I want to do is I want to take this 0.1 molar, and I want to calculate a pH off of it. So again, remember what our pH relation is. We can do this easily on the bottom. I have plenty of room. pH is the negative log of the hydrogen ion concentration. So in this case, the negative log of 0.1, or to make it a little bit easier, I'm going to write it as 1 times 10 to the negative first power. Now remember what I said about logs. Log is the opposite action of taking something 10 to the power. Those will cancel. The negatives will cancel, and I'll find that the pH of this solution is 1. So if I have a 0.1 molar solution of hydrochloric acid, I have a solution that has a pH of 1. That means, guess what? It is, look at hydrochloric acid. Notice it is a very strong acid. Now, one other thing we want to notice, because this is a log scale, let me clear ink and move this scale over. What I'm talking about when I'm talking about hydrogen ion concentrations is we are talking about exponential numbers. So what this is telling us here is this is the concentration of hydrogen ions compared to distilled water. So again, in distilled water, there's 1 times 10 to the negative 7th. Well, if we go up to a pH of 6, that means it has 1 times 10 to the negative 6th molar. Now, it doesn't seem like a lot, but that is 10 times stronger than neutral water, right? These are exponential values, so they increase by a power of 10. If I go up to a pH of 5, and it sounds weird talking about going up when our numbers are going down, if I go to a pH of 5, again, my pH of 5 is 1 times 10 to the negative 5th molar concentration. Again, that's an increase by a power of 10, or an increase of a power of 100 over neutral water, so it's 100 times stronger. So acid rain, even though it has a pH that doesn't seem super strong, a pH of 5, acid rain is about 100 times more acidic than neutral water. So it is a power of 10 scale. So if we went down one more step again, now we have a pH of 4. A pH of 4 would have 1 times 10 to the negative 4th molar concentration of hydrogen ions. Now that is 1,000 times stronger than neutral water. Again, a power of 10 times 10 times 10, that's 1,000 times stronger. So when we're looking at the pH scale, always important to remember that it is a log-based scale. So every time we go up a step, we are increasing by a power of 10. Not a power of 1, by a power of 10. So you may have noticed I was just in my head magically switching those pHs into hydrogen ion concentrations. Now, how did we do that? Say if we have that pH now of 3, well, what is the hydrogen ion concentration of that? Well, I gave you an equation to calculate the pH from the hydrogen ion concentration, but not the other way around. But we can easily rearrange this equation. Now notice pH is the negative log of the hydrogen ion concentration. If you rearrange this, again I said the opposite action is taking something 10 to the power. Notice I'll have to have 10 to the negative power to cancel out the negative log here, and I'll have to have 10 to the negative pH over here. So we can calculate hydrogen ions from pH. It's really, really easy. The hydrogen ion concentration of any acid is going to be equal to 10 to the negative pH. So if I have a pH of 3, the hydrogen ion concentration is 10 to the negative third, which we could represent as 0.001 or 1 times 10 to the negative third. So switching between pHs and hydrogen ion concentrations really is not terribly difficult, especially if we're talking about values to the 1. We're just talking about exponential values, powers of 10. If we're just talking about powers of 10, very easy. If we switch into more values that aren't simple powers of 10, it gets a little bit more complex, but that's when we go for our calculator. One other relationship I want to show you. So we already talked about this, that the Kw is always the hydrogen ion concentration times the hydroxide ion concentration. So for instance, in this example, if my hydrogen ion concentration is 10 to the negative third, and my Kw is 1 times 10 to the negative 14th hours, this is 1 times 10 to the negative third, well then I can solve for the hydroxide ion concentration. So again, my hydrogen ion concentration now is greater than 1 times 10 to the negative 7th, so the hydroxide should have gone down and be smaller. If we rearrange the equation and solve, we'll find our hydroxide ion concentration is 1 times 10 to the negative 11th. Again, the product of these two values always has to equal that 1 times 10 to the negative 14th at 25 degrees. And we're going to assume all our acid-base reactions are happening at room temperature or close enough to room temperature that we can use this relationship. Very, very last thing we want to talk about is there is also something called the POH. That we don't use the POH as much, we don't reference it as much, but it is a similar calculation. We can take the negative log of the hydroxide ion concentration, and that will give us our POH values. Our POH of this value, notice the POH of this hydroxide concentration, if we put this value in, again, we use it just like we use the equation for pH, except for solving for the hydroxide ion concentration. The POH here is 11. Now notice what we have. The POH is 11. Where did we have it? The pH was 3. And so I can represent one more relationship for when we do acid-base calculations. pH plus the POH for any solution will always equal 14. So if we know one, we know the other. So all we need to know is one of these pieces. In any calculation, if we have the pH, the POH, the OH, or the hydrogen ion concentration, we can solve for the rest of them because we have our sets of relationships. We know most importantly that the Kw is the product of the hydrogen ion concentration times the hydroxide ion concentration. It always equals 1 times 10 to the negative 14th. We know that the pH is the negative log of that hydrogen ion concentration. We know that the POH is the negative log of the hydroxide ion concentration. We know that the sum of the pH and the POH is always equal to 14, and that's really all we need to know. If we want, we could write down the relationship that the 10 to the negative pH is going to be our hydrogen ion concentration. We can rearrange that equation, and likewise 10 to the negative POH will always give us the hydroxide ion concentration. So with those relationships, I think we can solve some of the problems that are in the section review at the end of this unit. Okay, before we do that, a couple of things from your book that we just want to be aware of. Notice I said we were talking about the Kw of water at 25 degrees, and that's the relationship we use. Notice it does change at different temperatures. As we go up and our temperature gets greater, now we have doubled the temperature, notice the Kw has also increased. So what we have in that instance is basically water's ionizing itself more at higher temperatures. At lower temperatures, the opposite is going to happen, so there's less ions in solution. Again, we're using the 1 times 10 to the negative 14th in all of our calculations, assuming 25 degrees. Just know it's a constant at a certain temperature, but it does vary with temperature. The other thing we want to be aware of is when we're doing these calculations, we are talking about things that are strong acids or strong bases. Again, strong acids or strong bases completely disassociate or they completely ionize water. So like in our example with hydrochloric acid, say we had any of these strong acids, say we have nitric, because we use nitric quite a bit. If you have a 0.01 molar solution of nitric acid. That is going to completely ionize water, and we'll have a 0.01 molar solution of hydrogen ions, or in our case, we could also say, again, hydronium in solution. So those are going to be equal. We can just assume the acid concentration is the hydrogen ion concentration or the hydronium ion concentration. Now, that's not going to be true if we talk about things that aren't strong acids or strong bases. So right now we can do this. Let's be careful as we go forward that we'll have some weak acids, some weak bases, and we'll have to change our method slightly. The other thing we need to know is, if we look at these, we have strong bases here that all have hydroxide. That works the same way. If I have a 0.1 molar solution of lithium hydroxide, I have a 0.1 molar solution of hydroxide ions in solution. Where this changes, though, is if we have something like calcium hydroxide. If it is CaOH2, if we have, say, a 0.1 molar solution of CaOH2, what hopefully you recognize is that calcium hydroxide has two hydroxides, so our hydroxide ion concentration when this gets dissolved in water is actually 0.2 molar. So something we'll just have to watch for if they have one of these species. It's still a strong base, but we'll have to double the hydroxide ion concentration because it will completely dissociate. This, again, from your book, is our relationships that we currently have for neutral water. The hydrogen ion concentration and the hydroxide ion concentration are equal. The pOH and pH are equal. Both of those concentrations are equal to 1 times 10 to the negative 7th, and the pH plus the pOH, not plus, they both equal 7, so their sum would be 14, and their sum is actually always 14, right? In acidic solution, we already said this, the hydronium ion concentration is greater than hydroxide, the pH is less than the pOH, the pH has to be less than 7, the pOH greater than 7, the hydrogen ion concentration greater than 10 to the negative 7th, hydroxide ion less than 10 to the negative 7th. Okay, I think we have these relationships. Let's do some problems. Okay, so a couple of questions here that hopefully we know. What is the concentration of hydronium and hydroxide in pure water at 25 degrees? That was on that previous page, but that is the 1 times 10 to the negative 7th. Why does the pH scale range from 0 to 14? Again, it's based on the kW of water. All of these solutions are happening in water. So our pH scale, again, and this is at 25 degrees, but it's based off of our maximum value being the kW of water, which is the 1 times 10 to the negative 14th. So that's why our scale can go from 0, rarely get to actually 0 to 1 times 10 to the negative 14th, or 214, I'm sorry. What else now? Why does 7 represent neutral solution? Because the hydrogen and hydroxide ions are neutral. Now, all right, some actual problems we can do. So the question 4 is asking us to identify which is an acidic or basic solution here. Well, A is acidic because this concentration is less than greater than 1 times 10 to the negative 7th. So there's more hydrogen ion concentrations. That's an acidic solution. If I look at B, now the hydroxide ion concentration is greater than 1 times 10 to the negative 7th, so that is a basic solution. We could really quickly calculate the pH of these values. The pH of the first one, again, is the negative log of that hydronium ion concentration, or hydrogen ion concentration. So the pH of the first one is 3, which makes it acidic. What's the pH of the next one? We have to be a little bit careful. I can directly calculate the pOH, which is the negative log of the OH, and this is where people screw up, is they want to just calculate the pH based off this, but this is the OH concentration. So I first have to calculate the pOH. The pOH of that value is going to be 4, and if the pH plus the pOH equal 14, and again, my pOH is 4, that means my pH is 10, which again is above 7, so that is a basic solution. A couple more here. pH of 5 is less than 7, so that's acidic. Again, I could calculate the hydrogen ion concentration off of that really easy. It's 10 to the negative pH, or in this case, 1 times 10 to the negative 5th, which again is greater than negative 7th, so it is acidic. pH of 8, again, that would be basic because the concentration is less than 1 times 10 to the negative 7th. Okay, some other calculations here, hopefully. Let's see. A solution contains 4.5 times 10 to the negative 3rd hydrochloric acid. Determine the following for the solution. Well, if we look at this solution, Again, this is hydrochloric acid. We have to recognize that's hydrochloric acid. That's a strong acid. So this concentration will also be the concentration of the hydrogen ions, or like we like to say, the hydronium ions. So this is the answer to A. If we have 4.5 times 10 to the negative third hydrochloric acid, we have 4.5 times 10 to the negative third hydrogen ions, or again, more accurately, hydronium ions. However, now what's the concentration of hydroxide? We'll have to use our Kw relationship for that. Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. I will plug in my hydrogen ion concentration, rearrange for hydroxide. So I'll have hydroxide equals my Kw, which is the constant 1 times 10 to the negative 14th. We'll assume these are all at 25 degrees, divided by 4.5 times 10 to the negative third. 1 divided by 4.5, I believe, is about 0.22 times 10, negative 14th minus a minus 3. We have to add it. We get negative 11th. So my hydroxide ion concentration, 0.22 times 10 to the negative 11th, or 2.2 times 10. This value just got bigger. This needs to get smaller, negative 12. So that's my hydroxide ion concentration. Last piece. What is the pH? Well, now we actually have to use a calculator, unfortunately. The pH is the negative log of, again, the hydrogen ion concentration, which, again, in this case is 4.5 times 10 to the negative third. Unfortunately, if it's not just a power of 10, now I have to use my calculator to do the log. I do know that the pH is going to be around 3, probably a little bit below, so I get an answer of 2.3. Now, notice when we have a value like this, we can't do it straight from what the exponent is, but the exponent still gives an idea of what our range should be. So we get a pH of 2.3. If we want to go one step further, we could also calculate the pOH, because the sum of the pH and the pOH always have to equal 14. So in this case, our pOH would be, what, 11.7. All right. So we might have to use a calculator if we, again, don't just have base 10 values for pHs, but that's not a huge problem. We still just plug it into the equation we calculate. One other one here, and I want to do it because there's a little trick. Now, we have a calcium hydroxide solution with a pH of 8. So it's giving us a pH of 8. Determine the following values. What's the hydronium ion concentration? Again, the pH is the negative log of the hydrogen or hydronium ion concentration. Thus, if we rearrange that again, the hydrogen ion concentration is 10 to the negative pH. So it is 1 times 10 to the negative 8 is how I'll represent it. That is my hydronium ion concentration. Notice it is smaller than 1 times 10 to the negative 7, so this is a basic solution. My hydroxide ion concentration, again, using our Kw relationship of hydrogen ions times hydroxide ions, that will give me a hydroxide ion concentration of 1 times 10 to the negative 14th, divided by, when I rearrange it, 1 times 10 to the negative 8th. So my hydroxide ion concentration is 1 times 10 to the negative, adding 8 to it, negative 6th is my hydroxide ion concentration. Thus, if I wanted to do the pOH really quickly, the pOH would be, let's see, the negative log of that hydroxide ion concentration, or a pOH of 6. Now, just to check, my pOH is 6. My pH was 8, so they do add up to 14. Ooh, look at the little trick here. Now it says, what is the concentration of calcium hydroxide? Well, notice, this is the concentration of my hydroxide ions is 1 times 10 to the negative 6. But each calcium hydroxide would give us 2 hydroxide ions. So if I want this concentration, actually what I have right here is a concentration of hydroxides. If I want my concentration of calcium hydroxide, I'll have to divide that by 2, because 2 of them bond together to make that calcium hydroxide. So 1 times 10 to the negative 6 divided by 2 would be 5 times 10 to the negative 7th molar.